Today we're going to be talking about relays, fuses, transformers. So we get a little better understanding of what these components are and what they do in the circuit. We're going to start with the transformer. We have two different type of transformer here today. There's a little bitty one and there's a big one. Now this big one that we have, it is a step down transformer. What it is, that means you have a high voltage on the input side, you're going to get the low voltage on the output side. A step up transformer. These transformers are used to increase the voltage. Mainly you're going to see that in the ignition coils or spark igniter systems or equipments like that. Then they use in a transformer for stepping up the power to get the use out of it, mainly for a spark, and like I said, in the spark igniter heating systems, or like ignition in your car. That's what they're using. They're using that little one to step up the power to be able to create a spark for the ignition to happen. Now we're gonna be mainly dealing with the step down transformer, and we don't want to talk about that one. So how transformer works? Your main power goes through these wires. Two of these wires, whichever it is, goes through a series of a coil that is just a lot of wire, very, very tiny wire, as you can see in there, and is wrapped around this iron core on the inside. Power goes in there, create a magnetic field, and that magnetic field is going to get transferred to the secondary of the transformer. And when that happens, it's going to create a voltage on the secondary and it's going to come out. Now, this is called a step down transformer because you have a high voltage input, low voltage output. Your output is going to be lower than your input. That's why it's called step down transformer. And as you can see on this one, we have tri-voltage transformer. If you use the black as an input, as a common wire, this wire, with the white one, you can get the 120. You can use it in 120 circuit and you get 24 volt out of it. Now if you use the black with the orange on the 208 circuits, you can get 24 volt out. And if you're using the black one with the red one at 240 powers, you are still gonna have 24 volt. There is a set of wires and it just goes around, and it has some different tabs coming out of the transformer for that purpose. So between the first wire, which is your common black, and the last wire, which is the orange, that's your beginning and the end of your loop. So if you want to check this transformer to see if it's good or bad, you're gonna put your ohm meter on the ohm reading, and one wire to the orange one, you got to make sure there is no power to that circuit first. That's very important. You're gonna check between orange and black. Let's see if we can get that ohm reading. There we go. We have 76.4 ohm. And if you don't get that reading between the first and the last wire in the circuit, that means the wiring inside is burned out, is open. Same thing on the output. Again, that's just another loop of the wire, then it goes completely through transformer. So you want to check the output as well, and when there is no power to the transformer, you should read a very, very low ohm reading. And if you do, most likely your transformer is good. It could be still used. Fuses. Fuses are very simple items. Imagine this is our system. Is a chain. Electrons is going to flow through. Now, can you spot the weakest point on this chain? As you can see, the rest of the chain is pretty hefty, but just the top part of it is not. That's exactly how a fuse is designed. So when the electron is moving through and the pressure inside the electron is getting inside the wire is getting higher and higher and higher, the fuse is going to break apart, and that's it. Is the flow of the electron is going to stop. Electrons coming out of the transformer, traveling into the board, goes back in here, everyone's are happy. Now, according to Ohm law, the higher our resistance, the lower the amperage is going to be. Amperage and resistance are always working opposite of each other. That's why the fuse is not blowing up, wires are not melting, everything is good. This board has a very high resistance if you check these terminals with the ohm meter. Now, what happens when the wires are touching each other, or one of the wires accidentally is touching the ground or rubbing on the side of the cabinet inside the system because the unit is vibrating when it's functioning? This is what happens. That's exactly what it is for. It's the weakest point of your wiring. The fuse is there just to burn itself, sacrifice itself to prevent any kind of damage to your source, wiring, or anything else. The fuse goes out so nothing else burns out. So anytime you see a burnout fuse, always check, see what was the cause, what wire was the problem, which caused that failure. Can control the high voltage equipment. Like we say, we have a control board and it works off of the 24 volts or 3 volts or 5 volts. It doesn't matter. The controls never need a high voltage for operation. The controls are always going to be running on the low. Now, the control, to be able to control components that they are running on the high voltage, you're going to need the relays. A contactor is a relay. Ice cube relay is a relay. These little bitty ones that you see them on the control boards, they are relays. That's what they do. How it works is the main power is coming in to the input of the relay. It depends on, some of the relays are a little different design, but they all doing the same thing. And your load is going to be on the outside of on the outgoing side of the relay. Most of the relay do not have a polarity, so it really doesn't matter. And when you have the power and everything ready, and when the controls that you have on that end, the control board is calling for whatever component to come on, it could be a compressor, a motor, a blower motor, a relay, whatever the case be, that relay closes, and here we go, that motor is running. And as soon as the control side, which is over here, is disconnected, that load gonna stop. Now we can see we have another little complicated type of relay in here. These are not really complicated. As soon as you understand what the relay is, there is no relay on the planet is complicated to you. We have multiple legs on this relay, as you can see. This one is very easy. There is only one channel on this side, one channel on that side. Power comes in, waits right here at these two terminals till the control is applied to both sides of this relay, over here and over here. And as soon as it has voltage to these parts, this coil then you see at the bottom is going to create a magnetic field which is going to pull down on these two at the same time. And when that happens, there is a bridge on the top that is going to let the electrons to pass through. And that's what you're going to hear, a loud pop every time this relay comes on and your load is running. And when it stops, the motor will stop. This one is double through single pole type relay. There is two input, two output, but there is only one pole it required for the power to goes in. And that one is always normally open type relay. This one, on the other hand, it has the same design. As you can see, this blue part of this relay is that same magnetic coil that you see over there. The only difference is this one, it has a normally open and normally closed points. So this is our common terminal. As you can see, there is a wire. It comes all the way up here and it connects to this spring. And this spring has a little point of contact right there. And you probably can see this is moving. This is going up and down. It has two set of these. This relay has a normally closed and a normally open contacts. Now, what does that mean? Normally closed is the one that is closed when the relay does not have any power applied to the coil. Imagine it's going to be like this all the time. The common terminal is the blue one, and normally closed, and this relay is on the top. Let's see if we can get a good. As you can see, it's reading 0 ohm between this one, which is going all the way through, and this one, which is coming out, is 0 ohm. And this one, you see there is a little bit of gap right there. You can see this one can go up and down. There is a little bit of gap right there. So electrons, they comes in, they go all the way here. They can go easily to this point, but none of them can go here because there is a gap right here. As soon as you supply power to these two, this coil, this magnet will energize and is pulling this one down really hard. And when it does that, it's going to closes this to this terminal now, and the gap is up here right now. So now this one, there is nothing can pass through that terminal. That's what is called normally closed, because when you check it right now with no power to the coil, is 0 ohm, and the other one is normally open. Sorry. And when you check this one right now, or this one, is nothing. Now, if I'd be able to get these two together at the same time with one hand and pushed on this contactor to close it, you can see now ohm meter, it shows 0 to that leg. And when I let it go, it goes to OL infinity. Now, one more time, normally closed is the one that is closed with the common terminal when there is no power is applied. And normally open is the one that again is open when there is no power applied. Some of these relays, they're gonna have a marking on it that it says normally open or normally closed. This one doesn't, so you have to either check the manufacturer specification on it, or just you can see through the glass like this one and check what contacts are what. It's sometimes hard with the ohm meter to check this out. A lot of time I like to pop the cover out of them. If there's a black cover and you cannot see inside of it, I like to pop it out and take a look at the terminals myself, just to be verifying before I supply the high voltage power to the equipment. Relays are very simple, very easy to use. Now, what happens when this relays goes bad? a lot of time you're gonna go see when this point of contacts, every time this relay opens and closes, there is going to be a small arc is happening between these 2 points of contacts every time. After a few years of usage, these arcs, they're going to cause an oxidation right between those 2 points of contact. And the oxidation that is going to happen is going to cause that electrons that is trying to pass through, they're having a hard time passing through. They act like a resistance. And when that happens, those 2 points of contact, they're going to start overheating. And at one point, when this contact closes, there is enough of heat is going to generate in between those contacts that is getting welded shut. And when that happens, when the power is disconnected from the system, and now the system should be shutting off, since this one is still closed and it is welded shut, the power constantly going through. If it's a fan motor for something, it's not going to cause a whole lot of problem, just the fan going to run all the time. But if that happened to a compressor or a part of the system that it require everything else to be functioning at the same time with it, that easily going to burn out your equipment. So always what you want to check for in any relay that is actually visible, sometimes they have a dust cover on it. That's pretty much that's what it is dust cover. Because dust, when they get inside the contacts, they're gonna cause a resistance. You want to check to see if those contact points are clean or they burned, they blacked out, or whatever the case is. And if you see that they have a sign of being arcing, that relay is gone. The main reason these relays are sealed from factory like this is because of that. The less moisture and dust and everything else you have inside it, these relays going to last a longer life. Now, what happens when this area is going to get arced out and is going to get blacked out? This is what's going to happen to the relay. I'm going to loosen one of the terminals. Now, we want to take a look at this and pay attention what happens. Right now, the motor is running. No problem. Everything is good to go. When those contacts are getting damaged, they're going to have this effect to the motor. Can you hear it? The RPM is keep going up and down. And you can see the amperage over there is keep jumping up and down. The voltage is always going to be the same because it's coming from the generator. But your amperage is what is changing. The more arc you have, the more resistance is going to get added. Your motor is now struggling to run. And at one point, that's it. You're going to stop. But when that happens, since that motor is always under a load, it's going to be a lot of pressure you're going to put on the motor to run, especially when it's a compressor. That's an easy way to burn out the compressor. If there is a bad relay, arced out or burn out points, always change it out. I want you to see what happened to this coil. Did you see that? This is going to be the power that is coming from the main breaker. They go to the bottom of the contactor. They just wait till there is a signal wire coming in from your controls, which is thermostat, control board, whatever the case might be. And here you go. Your compressor, your motor, whatever it is going to be running and running and running till the thermostat satisfied and it will stop. Sorry. There we go. This side of the transformer, the voltage is not deadly. It's not going to do you anything if you touch it with your bare hand. The other side, on the other hand, you touch it, you're not going to be alive to tell someone else what happened. So always be careful when you're working with the high voltage. Same thing on this relay. Now, what we talked about, as you can see, we have these two are our relay coils, and these are our common normally open and normally closed. I want you to look at this terminal right there. That's what happened when the power is supplied. See that? The normally closed contact going to be normally open as soon as the power is energized, and the normally open going to be closed. As long as you have power going into relay, the electrons will flow through. They go do the work for you, and the second power disconnected, that stops. Okay, so this is for today. I hope we all learned something today. Now we know what the transformers are, we know what fuses are, and we know what relays are. If you have any questions or comments, put it down below, and I will respond as soon as I can. Thank you.